This is Bill Farmer again. Welcome to McMaster University course, Computing and Software 701, Logic and Discrete Mathematics. We're going to continue talking about the topic of simple type theory, and today we're going to talk about the expressivity of simple type theory. So we have presented the syntax and semantics of two versions of Alonzo, core Alonzo and full Alonzo. Recall that Alonzo is a version of Church's type theory, which is a version of simple type theory. And the first thing I want to say is that we can prove a theorem that says there is a faithful interpretation of nth order logic in core Alonzo for all n greater than 1. So faithful interpretation means basically we can embed nth order logic into core Alonzo and have it work just the way you would expect nth order logic to work. In particular, we can embed first order logic. So core Alonzo includes first order logic effectively, second order logic, third order logic, and so forth. This makes it very expressive theoretically. Now the other thing I want to say is that what I'm going to try to show a little bit today is that most mathematical notions can be directly and naturally expressed in full Alonzo. This is one of the virtues of full Alonzo. We can express mathematical ideas naturally and directly. So Alonzo has great theoretical as well as practical expressivity. So theoretical expressivity is what you can express in any way. Practical expressivity is what you can express in an easy, direct, readily done way. Okay, so I'm going to show you some very simple examples. These are examples of three constants. The first is a constant which takes a relation. You can see here it takes a relation and gives back true or false. It takes a binary relation. And it gives back true if the binary relation is an equivalence relation, and it gives back false otherwise. So this is defined as a function abstraction. And basically the function abstraction takes a binary relation and it returns a conjunction, and the conjunction says that the relation is reflexive, symmetric, and transitive. And if you think for a moment, this is about as direct as you could possibly make a definition of a constant, which is a function that checks whether a binary relation is an equivalence relation. And it's noteworthy to point out we can't express this directly in first order logic because we don't have function abstractions, and we certainly can't quantify over predicates. The second example is the compose operator. It takes a function of this type, alpha to beta, and a function of beta to gamma, and returns a function of alpha to gamma. And we're thinking here of this function being curried. So here it is. It's lambda f, lambda g, dot lambda x, dot g applied to f of x. So the output for a function is right here. That's the function. That's the composition of f and g. Now notice that the order f and g here are being reversed here. We could have done it the other way if we wanted, but this is how I've done it. Once again, this is completely straightforward way of defining composition. It's exactly what you would expect composition to be. It's something we can't do in first order logic directly. The next example, which I know you've already seen, is is the inverse image of a function. So the inverse image of a set but by a function. Okay, so here's the function. Here's the set. So we take the function as input, we take the set as input, and notice that the set is a set of type beta, and then we return a set, and that's the inverse image, and that set will have type set of alpha. Again, this is a completely direct definition. There's no surprises here at all. It's just what we would expect if we were going to define the inverse image. And the syntax here is all the syntax of full Alonzo. Okay, now I want to go to a theory that we've talked about, the theory of Peano arithmetic. So this is Peano's original theory, which we can't express in first-order logic, but we can very easily express it in core Alonzo. So in this theory, we have a language that has one base type. I'll call it blackboard n, and I have two constants, 0 and a successive. And they have the appropriate types. And then we have the normal axioms, normal Peano axioms. 0 has no predecessor, which we write like this on the right. S is injective. And these two axioms effectively say that we're defining an inductive type or inductive set, and we have no confusion. That means that if we build up two different values from 0 and successor, we build up these two different values in two different ways. If we build two values in two different ways, the values must be different. And we have the induction principle, the normal induction principle, which we can call weak induction. And notice we can quantify, unlike in first-order logic, over, in this case, unary predicates. And this part handles the no jump part. No jump means that in our set, in this type, natural numbers, the only natural numbers are the standard natural numbers, 0, 1, 2, 3, 4, and so forth. There aren't any infinite natural numbers. And so there's a theorem that's due to Dedekind. He developed this theorem about the same time Peano came up with these axioms. And that says this theorem has up to isomorphism. So up to isomorphism means every model has the same structure, but we may name the components differently. So it has a unique standard model where in the frame, the domain for n is the set of natural numbers. So basically, this simple little theory has just one model. And that one model is the normal standard model of, I should say it's one standard model. It actually has many general models, but it's only one standard model, and that's the normal model of the natural numbers. So this kind of theory is said to be categorical. So categorical means it has only one model, one standard model. It's better to say categorical in the standard sense, as opposed to the general sense. Okay, so that is very nice. We can write a simple theory, and that theory will allow us to talk just about the natural numbers, not talk about any non-standard models, just let's standard model of the natural numbers. Now, as I've said before, we cannot do this. We cannot do this in first-order logic. The reason we can't do it is because we can't express the induction principle, the third axiom, in first-order logic. Okay, so we can't do it in first-order logic, but we can easily do it in core Alonzo. So now I want to look at another categorical theory, which I'm going to call COF. COF stands for, all right, well, it's right here, complete ordered field. And this is a theory of full Alonzo. We have one base type R, and we have a whole set of constants. The names are given here, and the types are given here. And below, I'm not going to put as subscripts the types and the names because we can see from this table what they are. So we have 0 and 1, we have negation and the inverse operation. We have a positive predicate, so when we apply that predicate to a real number, it's true if the real number is positive. We have normal plus and times, less than and less than equal, upper bound and least upper bound. Then we have as axioms, so that's the language. Now the axioms, we have 16 of them. Here they are. So what do these say? One says that addition is associative. 2 says that addition is commutative. 3 says that 0 is an identity element with respect to addition. 4 says that negation is an inverse operation with respect to negation. And we have the similar kinds of properties here for 5 through 8. It says that multiplication is associative, it's commutative. 1 is identity element with respect to multiplication, and the inverse or multiplicative inverse is an inverse operation with respect to multiplication. Except there's a little caveat here. And this caveat is that we must, this is only true if x is not 0. And then because we can talk about things being undefined, we can directly say right here that the inverse of 0 is undefined. So that means in particular 1 over 0 is undefined. And then we have here that 0 does not equal 1, and finally we have the distributive law. So all of these are the field axioms. They say that our theory is the models of our theory are fields. And basically the field axioms have just exactly the axioms we've said. So the real numbers, in other words, is a field. Now if we look at 12, 12 defines what the positive numbers are. Basically says every number is going to be 0, positive, or it's going to be negative. And then 13 and 14 say that addition and multiplication respect the ordering. So if I have 2 positive numbers, I add them, it will stay positive. If I have 2 positive numbers and multiply them, it will stay positive. And 15 basically, I said 12 defines positive. It just breaks up the real numbers into 3 groups. 15 says what positive means. So positive means, all right, let's put it this way. X is less than or equal to y. What that means is that y minus x is positive. No, actually, what I said isn't quite right. What I should have said is we can define x is less than or equal to y in terms of positivity. And we can define x is less than or equal to y in the natural way. And then 17 and 18 define what the upper bound and least upper bound are. And finally, 19 says, for all sets of real numbers, if S is not the empty set and S has an upper bound, then S has a least upper bound. And this axiom is called the completeness axiom. And we cannot express this in first order logic because we're quantifying here over sets of real numbers. So anyway, this, and I should point out that if we look at all the axioms up to, all of them up to here, this is a complete, I should say, no, this is an ordered field. So the first 14 axioms give us an ordered field. 15, 16, 17, 18 are definitions of these notions. And the last axiom is the completeness axiom. That's why we call this theory a complete ordered field. And the wonderful thing about this theory is that it has up to isomorphism a unique standard model. And that standard model, the domain for R, is exactly the real numbers. So this theory is categorical. It has basically just one model, the normal model of the real numbers. And once again, we cannot express this theory in first order logic because we cannot express axiom 19. Okay, so I'd like to mention a simple little exercise, and that is state this theorem in our theory of complete ordered fields. Okay, so we're going to stop here, and next time we're going to talk about a proof system for full Alonzo.